Hello everyone. Today I will introduce my research about comparison of deep neural network-based model for estimating the distributed representation of compound. This is the work with my colleagues Dr. Nathan Wood and Professor Ichise. Today's presentation is as follows. First, I will start with some introduction about work embedding, compound work embedding, and why do we need to create compound work embedding. Then, previous work on compound work embedding and their limitation is discussed. Next, we present the proposed method to learn the representation of compounds. To analyze the effectiveness of the proposed framework, we will conduct the experiment on two downstream tasks, namely noun compound interpretation and phrase analogy. Finally, I will wrap up the presentation with the conclusion and future work. Let's discuss why do we need to use the word embedding. Normally, in any language processing task, we need to make the sentence understandable to the machine. However, the machine cannot understand the language directly. So the current machine learning model can only understand number or vector. So we need the word embedding to encode the word into the vector. But what is the word embedding exactly? Word embedding are the vector representation of words that encode the linguistic information. The linguistic information could be semantics as male and female, syntactics as the verb tense, and about real-world knowledge such as country and capital. In this work, we want to create a vector representation for compounds such as Tokyo Station and robot arm. But why do we need the compound word embedding? Usually, there are two most popular approaches to get the embedding for the compound. First is to concatenating the constituent of compound. I consider we input the New York into the work-to-vec model, and it will output to 1 by 3 vector. Then we can concatenate these vectors into a single 1 by 6 vector and use it for applications such as classification. However, if we have New York Station now, doing the same process, we will obtain 1 by 9 vector, which is not suitable for the input of the classifier. So, concatenating approach cannot provide a fixed length vector for application. Instead of concatenating, we can average the embedding of constituents of the compound to get the fixed length vector. The process is the same as above. However, this is a very simple combination and not sure that it is suitable because the meaning of the compound can be more complex than the average. Previous work has learned the vector representation of compound in two ways, in-context learning and out-of-context learning. The in-context learning that is to learn the embedding from a raw text corpus by replacing the multiple compound by a single token. Then we can treat any compound as word and learn the compound word embedding by some model. However, the occurrence of the compound is very low compared to their element word, so this way cannot provide a reliable result. Another problem with this approach is how to identify the compound in the raw text, which is hard to obtain. The second way is out-of-context learning, or we want to use the embedding of the constituent to estimate the representation of the compound. Previous work have used additive and matrix weighting to combine the embedding for two-word compound. This approach is more reliable and can handle rare and unseen compounds. Nevertheless, with this approach, it is not possible to apply for arbitrary length compounds such as three-word compounds or more. In this work, our goal is to learn better representation for arbitrary length compound by combining in-context and out-of-context learning. And in summary, we make two main contributions. First, we propose a deep learning approach to learn the vector representation for arbitrary length compound. Second, we extensively analyze different architectures to see how they affect the representation of compound. Let me discuss about the proposed methods. First, let's consider the input, the United States. The first step is to learn the representation of the constituent and the compound on purpose using the in-context learning. Then we combine the constituent vector into the compound vector by using out-of-context learning. Let me discuss step 1 in more detail. To learn the representation of the compound in context, we replace the compound with a single token. Then we combine the new sentence with the original one and use the word-to-vec algorithm to learn the actual representation for compound and the constituents. The problem remains is to how to identify the compound in text. In this work, we took two features. The first is use the anchor or the hyperlink tag from the Wikipedia. The second is the part of speech tag where we detect the noun phrase and mark them as compound. Then the second step is to combine the representation. In this step, we want to combine the vector representation of each constituent W1, W2 to Wn in the compound. We have done that by fitting the constituent vector into the current recurrent neural network and use the output of the last work as the representation of the whole compound. The RNN network is trained by minimizing the Euclidean distance between the actual and the estimated representation of the compound. To further analyze the effectiveness of different architecture, and we extensively conduct an experiment with bidirectional RNN, LSTM, and GRU. We also apply the attention mechanism to this network. Finally, we apply the state-of-the-art architecture, that is, transformer model, as a compositional model. In the experiment, we analyzed estimated representation by our proposed method with the two downstream tasks, the noun compound interpretation and the phrase analogy task. Let me introduce the first task, compound noun interpretation. In linguistics, compound can be decomposed into head noun within the right mode noun of the compound, and any left word is the modifier of the head noun. The compound word interpretation task is to identify the semantic relationship between the head noun and the modifiers. For example, the M here is a member of the robot. The procedure of the experiment consists of two phases. The first phase, retraining phase. First, we use a large corpus, namely Wikipedia and Encoding, to obtain a large amount of raw text to learn the representation of the compound and the constituent in context. Then, we train multiple networks as a compositional model to output the estimated representation for the compound, which are more similar to the actual representation. In order to do noun compound interpretation, we use the retrained compositional model. The dataset used is the chart dataset, which has two settings. The chord range setting consists of 12 relations and the file range setting with 37 relations. Then we use the compositional model to obtain the estimated embedding of the compound. Finally, we use the multi-layer perceptron to classify the relation. Let me discuss the main finding of this experiment in the next slide. The table shows the performance of multiple comparison baselines and our approaches in different settings of the chart dataset. The first finding is that our approach is comparable with previous work on the compound embedding, while our approach can handle arbitrary length compound. Next, outperform average baseline. This indicates the need of modeling the compound embedding instead of simply average the embedding. Another finding is that concatenation is superior to other models, which suggests that concatenation maintains the most information. Interestingly, the result from the actual orientation which learned from a large corpus is very low, therefore they are not reliable due to the sparseness of data. The second evaluation is the phrase analogy test, where we want to identify the suitable phrase based on the semantic relation. This task is from the original work to web paper, where we have the famous example, the closest vector to the calculation, vector king minus vector man plus vector woman is vector queen. So we want to do the same task for the compound. So the closest vector to the calculation, vector Baltimore-Sun minus vector Baltimore plus vector Boston is vector Boston-Clark. The procedure of the experiment is similar to now compositional interpretation in the last experiment. In the first phase, the retraining phase. However, in the second phase, we only do prediction. We use the retrained compositional model to obtain the estimated vector for the phrase, and then find the closest vector to the calculation, Baltimore-Sun minus vector Baltimore plus vector Boston. This table describes the result of multiple architecture on the phrase analogy test. We use the information retrieval metric to do evaluation, namely mean reciprocal rank, hit at 1 and hit at 10. Overall, the model with attention mechanism, transformer, LSTM with attention, and GRU with attention achieve the best performance. We show the effectiveness of the attention to emphasize the most important part of the compound. The performance of the average baseline is reasonably good. That can explain why averaging vector is still popular in the research. Finally, we conduct the presentation. In this paper, we conduct a comprehensive analysis on several architecture of compositional model. An evaluation on two downstream sites confirmed the effectiveness of the compositional model in encoding useful information into the vector space of the compound. Complex architecture such as GRU, LSTM, and transformer learn better prediction for long entities, such as in the phrase analogy test. Simpler models such as RNN is more applicable to the downstream task where only short compound, 2 or 3 work in length as in the now compound infertilization task. The possible future direction of this research is to analyze the differences between the compositional compound such as robot arm to the non-compositional compound such as hot dog. Finally, thank you very much for your attention.